day, everybody. My name is Luc Pelkmans. I represent IEA Bioenergy, and the presentation that I will give is attractive systems for bioenergy feedstock production in sustainably managed landscapes. I want to thank the co-authors for this presentation, who are also responsible for the project itself, and they are from IEA Bioenergy Task 43, and that's Biljana Kulisic, Joran Berndes, Janis Dimitriou, and Mark Brown. So, as an introduction, bioenergy is quite an important part of the energy mix and will also be an important part of the energy mix in the future. And quite a lot of biomass will be needed also to fulfill that role. So we have to look into what kind of potentials do we have, what sustainable potentials do we have to provide this biomass. We look into different categories, starting from municipal solid waste, going up to residues from industry, from agriculture, from forestry. Also, additional forestry operations give some extra potentials. And also agriculture, so using land which is currently unused or underproductive. Altogether, this brings a certain potential, which is estimated somewhere between 100 and 200 exajoules, comparing to the global energy supply 2018 that was 600 exajoules, of which 10% was biomass. Now, for deployment of bioenergy, we will need all of those options, maybe not to the full extent, but we can't really ignore any of them. So we will need waste, residues, forestry, and energy crops, all produced in line with sustainable resource management, with sustainable forestry, good agricultural practice, and with minimized impacts on land use change emissions. It's best to co-produce that with other products, with food, for instance, using underproductive land or having improved production in agriculture, which, by the way, is also part of a general effort that we need to have an improved general agricultural productivity and efficiency. Now, this also fits in decarbonization scenarios, or scenarios to go towards net zero emissions of the energy sector. And here you see the role of bioenergy in a scenario that was calculated by the IEA in Paris. You see the role of bioenergy in different sectors. So in the building sector, which is also starting from traditional use of biomass, but which is switching more to the modern use of biomass. In industry, in transport, in power production, and also other energy transformation systems. So in this scenario, the role of bioenergy would increase from the 10% that we have now in the energy system up to 20% in 50 years from now. So it's an increasing role. It's kind of a doubling of the biomass that we need. So we need to have a serious mobilization to reach that. So that's kind of a conclusion of this, is that mobilization of sustainable biomass is really a prerequisite of the bioenergy deployment that we need. So we need a strong increase of the supply. It's kind of a doubling that we would need compared to today. Organic waste and byproducts are the most common feedstocks which are presented. They can make important contributions, but they will not be enough to meet the anticipated levels that we would need. So we would need dedicated biomass production systems for energy. And kind of the basis of this project is also to look into how can we integrate new biomass production systems in agricultural landscapes to provide feedstocks while at the same time also reducing current land use impacts and contributing to ecosystem services. So as mentioned, the basis of this presentation is a report which was developed by IEA Bioenergy Task 43 project. Task 43 is on biomass supply. There was a call system in 2017 and 2018 for people who could present attractive examples of landscape management and design that could help bioenergy and the bioeconomy, and then which would lead to a catalog highlighting worldwide examples of interesting biomass production systems throughout all stages of production. And all of them contributing to biodiversity and the generation of other ecosystem services. You see the link here where the report is available. There have also been a few workshops to discuss some attractive examples. In the report, you will find a number of contributions which were published. So you see 11 here. I won't go into detail in all of them. In the next slides, I will present a few of them, but we had an African case on agroforestry mainly. We had a number of Australian cases, then a number of European cases on biogas, on short rotation copies, fast-growing plantations, and also from the United States and Canada we had some cases. But I'll go through a few of them, but just looking into the general concepts that we see in these different cases. First kind of concept is using lignocellulosic crops on marginal and abandoned agricultural lands. So we're talking about short rotation copies, perennial grasses. So that's really something that really can make a big difference. Another example is introducing short rotation copies, so woody wood growth as landscape elements, using them for wind fences, using them for conservation buffer zones or in riparian areas. Another thing is crop rotation, so agriculture where you kind of integrate the production of energy crops through sequential cropping, that you also have a year-round soil coverage. Another was agroforestry, so that's combining food production with wood production, and mainly at a small scale level also. And another thing which was also as a case is unmerchantable trees and forestry residues. So I'll go through a few of those. So there was quite some studies on lignocellulosic crops and the crops on then perennial grasses like switchgrass and miscanthus, tree species like willows, eucalyptus, poplars. They're grown in relatively short rotations, so you can harvest every year or you can harvest every 5 years or 10 years, depending on how fast it grows and depending on what the system is. It can be cultivated on soils of varying qualities, so soils which are not the most fertile lands, but still reach relatively high yields. And it's important to look into site location, design management, and system integration, and you can really offer additional ecosystem services for that. And that in turn can also create added value, which is also important. Potential benefits of using lignocellulosic crops is that you can reduce soil erosion, so the land is covered all year round. There's also specifically in hilly areas that you can reduce runoff through rain when it's raining. You can stimulate accumulation of soil carbon in soils. You can have a stable nutrient cycling and soil activity, a better biodiversity when you compare it to other typical conventional crops. There's also bioremediation potential. For instance, willow, if you have contaminated lands, they can absorb some of the contamination. And some of these crops can also be used for treating nutrient-rich municipal residues like wastewater, sewage sludge, and act as vegetation filters. This is an example of a wastewater treatment in Sweden, in Enköping. So you see a view here. The picture was taken from the roof of the heat and power plant, which was next door. So you have a wastewater treatment system with wastewater ponds. Behind the ponds you see willow fields. It's 76 hectares of willow fields that are kind of used as vegetation filters for the water also. And at the same time, then it's producing biomass, which is then used by the CHP plants. So it's quite an interesting case. Another concept is on the idea of biogas done right in Italy, which is starting from the idea that we can produce food, feed, and biomass with sequential cropping. So it's more than just producing bioenergy. So you harvest 2 crops instead of 1 on the same field. You have a year-round crop coverage also. There's also a lot of focus on fixing carbon in the soil. on recycling nutrients back through this biogas system, where you have the digest state coming out next to the biogas, of course, and this digest state is then fed back to the land. And there's a combination made with agricultural systems to promote carbon sequestration in the soil. So you store much more carbon, and you also have, next to the carbon storage, you have this energy production. Another case, I'll highlight a few points. It's agroforestry, a case in Zambia, where you have some projects which try to promote integrated practice to improve food and energy security in these regions. And part of that is agroforestry, so growing wood next to food crops. There's quite a lot of benefits there. It's social benefits that you make, that you create extra employment in rural areas. You empower them. You have an increased income in these areas. It's also good for women, elderly, and disabled. There's economic benefits because you have, through these integrated systems, you have an improved agricultural productivity. It's really increasing food production. It's increasing output for livestock. So it creates business opportunities in rural areas. There's a reduced use of fossil fuel, the reduced use of fertilizer, and it's really developing rural infrastructure. So overall, a lot of environmental benefits, so reducing carbon emissions, of course, reducing land degradation, reducing soil erosion, enrichment of soil nutrients, and reducing the use of chemical fertilizer, because the crops, the woody crops, are also providing some of the nutrients for the land. Another example I'd like to highlight, last one, is concept of unloved trees, which is a nice word in Canada. So what you see is actually the combination with forestry. So there is a forest industry network in highly forested regions like Canada, which also need to adapt to very variable wood quality. And often these sawmills, pulp mills, they have strict standards and strict requirements in terms of wood quality. So there's always wood fractions which are unfit for conventional wood products. And it's not only tops and branches, but also it's part of the stem wood also, which is not suitable. So you can have tree sorting processes. You can use the degraded wood for biofuels, and the sound wood then goes to lumber. And if you don't do that, of course, then the counterfactual is that these degraded trees are left on the field as residues. So these trees, these unloved trees, can then serve as sustainable feedstock for bioenergy. It's quite a good opportunity, and also it's a sustainable feedstock when they help to unlock stands with a proportion of sound trees for sawn wood. So taking them out can also be a good practice of increasing production and yeah, kind of clearing the land to have new trees growing there, and bioenergy can then be considered part of an integral part of forestry systems. And an important point, message here was also that there shouldn't be a policy discrimination against whole trees for bioenergy, because some of the trees are indeed not usable as for lumber. So I would like to conclude with the takeaways from a project that we had. So first takeaway is that we need bioenergy deployment in long-term decarbonization scenarios, and this will require a strong increase in supply of biomass feedstock. We also need dedicated biomass production. It's not only cannot only be done with residues, so there will be a need for dedicated biomass production. And in this biomass production, we need to recognize synergies with other goals that we have. So you have climate action also, but you also have circular and sustainable bioeconomy. And a very important part is that you also have sustainable land management that you have to take as a basis. So there's a lot of benefits of integrated practices, so different goals and services. So first first is that you have energy biomass. Of course, it contributes to a shift from fossil fuels, but you also contribute to rural development. You contribute to synergies with food production. If you integrate it in agricultural systems, you can have reduced land degradation, an increased tree or plant coverage, reduce soil erosion. You can enrich the soil with nutrients and have an enrichment of soil carbon. And landscape elements can also reduce soil erosion between fields. It can create buffer zones to protect or improve biodiversity of high biodiverse areas. It can reduce nutrient spill off. It can remediate soils. It can act as vegetation filters. So there's quite a lot of extra benefits that you can have next to bioenergy. So it needs to be considered in an overall landscape management, and that's kind of the base message that I would like to have. So I would like to thank you for your attention. You're also welcome to follow another session, the technical session 22, which is on innovative landscape approaches for sustainable bioenergy. It's organized by IA Bioenergy Task 45, which is on sustainability. And for now, I would like to thank you for your attention. Thank you.
Hi, my name is Carlos Eduardo Cerri. I'm a professor at the Luiz de Queiroz College of Agriculture as part as the University of Sao Paulo. It's a great pleasure for me to have the chance to present in the BBEST 2021 under the section 16, Land Use for Biomass Production, the work from our group here that is titled Payback Time for Soil Carbon and Sugarcane Ethanol. So, as you know, Brazil wants to increase ethanol production, and there are many options for that. Basically, we can have new varieties in production of second generation ethanol. This is under development. As you know, it takes time. And the other main option is related to land use expansion. So those are the main options. And I'm going to talk about this last option here on land use. As you know, we should not convert any native vegetation. We should not clear any new native vegetation. So the idea here is to show you some results of the conversion of pasture to sugarcane and also from annual cropland to sugarcane. The main question here to be addressed is how much is the carbon debit? The payback time due to this conversion of land use from pasture to sugarcane, annual crop to sugarcane. So the idea here is to say, to show you a soil carbon balance after land use change. Imagine here the main land use change is pasture. So we have an amount of carbon stock here. And for the conversion, as you can see, part of this carbon is lost to the atmosphere as CO2 because we are plowing the soil and oxidizing carbon to the atmosphere. So we have a debit related to this land use. But we are including now sugarcane, and the crop residue is decomposed, and carbon stock is increasing according to management practices, soil type, and climatic conditions. So the idea here is the amount of carbon can be increased to pay this debit, and in some case even have a additional storage, a carbon sequestration. So this is the idea to show you the data, and also at the end to calculate the payback time, taking into account that sugarcane is used for ethanol, and ethanol is offsetting a fossil fuel, gasoline, diesel, and so on. So when we do that, as you know, we are reducing the carbon footprint and reducing greenhouse gas emissions to the atmosphere. Of course, it depends on how you cultivate sugarcane, but I will not have time in this presentation to address that. But I would be happy to discuss this afterwards. So the idea here is to show you the payback time, just to make sure here kind of a definition about what we are talking about payback time. So it's the time span that the conversion of a specific land into sugarcane, it could be pasture, it could be annual crop, as I said, would need to compensate emissions resulted from land use change, considering the offset associated to the replacement of fossil fuel by the sugarcane ethanol. So this is the payback time we are talking about. How we calculated that? The methodology we used was from the IPCC. As you are familiar with, we had to identify comparison soil pairs. We did the soil sampling, and we determined not only carbon content, but also bulk density to be able to calculate carbon stocks. And the estimated emission or accumulation was based in a tier 2 approach from IPCC. So we concentrated our activity here in the center south part of Brazil. We did not take into account the northeast part, but here in this region, as you know, we have the majority of the sugarcane cultivated area. In this region, we identified pairs of comparison, and we opened soil profiles to sample soil and under pasture or annual crop, and also side by side a sugarcane area. So we opened 9 soil profiles and took samples from the first 30 centimeters and also till 1 meter depth. So it was a large amount of work doing the conversion of pasture to sugarcane. This represents about 70% of the conversions. Annual crop to sugarcane, about 25%. And also, we took some areas of conversion directly, native vegetation, in this case of Cerrado native vegetation to sugarcane. This is less than 1% of the conversions nowadays. So what we did, just to illustrate for you, having a very fast idea, we opened a profile, in this case is the pasture, but the same was done in the other land uses. We took samples for bulk density and for carbon content analysis in different layers to, as I said, 1 meter depth. We took all these areas into account, so we could identify 135 sites we have sampled, representing 75 pairs. So those are the pairs: pasture converted to sugarcane, annual crop converted to sugarcane, and cerrado converted to sugarcane. In total, we had more than 6,000 soil samples that we have to process in order to calculate carbon debit. So basic information also from these sites, we got management practice, if it was burned sugarcane or unburned for harvesting purpose, the soil type, texture, climate factors, the time span after land use change. All this data was also taken into account. And now I want to, because our time is very short, I have to jump for the results. And the way we are going to show those are in response ratio. So the unit is tons or megagrams of carbon per hectare. So the idea was to compare carbon stocks under sugarcane and the reference. The reference, as I put here, could be pasture, could be agriculture, row crop, or cerrado, the native vegetation. And the way, as you know, to interpret that is, if we have values lower than 1, this means that we are losing carbon. We have a soil carbon reduction. If the values are higher than 1.2, for example, you have 20% increase, so a carbon storage. And when you have the crossing point here in 1, there is no change. We took into account the number of years necessary to reach this condition, and we call that, as I mentioned before, payback time. So we have done this in pasture, cropland, cerrado, as you can see here. In some of the cases, we gain carbon if the pasture is well managed. Sometimes if we lose carbon, the same for cropland. And those are the data here. The green means we have an increase, a carbon storage, and red means we reduced soil carbon stocks for 0 to 30, 0 to 100. This is for pasture, the same idea for cropland. You see they are almost even here. And the native vegetation, we always lose carbon when we convert cerrado to sugarcane. So putting all this data together and taking into account other data, as I mentioned before, like the management practice, soil type, and so on, we derived land use change factor using a linear mixed effect modeling approach. Again, I'm sorry, I have no time to describe that, but I would be happy to discuss afterwards with you if you are interested. So those are the results, the land use change factors for 30 centimeters of the soil. As you see here, if you have lower than 1 values, this means that we are losing carbon. If you have 1.10, for example, here, means 10% of increase in soil carbon. We have done this in different time spans, 5, 10, 15, and 20, but we are taking into account 20 years, as recommended by the IPCC, in which we supposedly reach a new steady state. So this was done for pasture, cropland, and cerrado, as I mentioned before. So using this data, for cerrado, when we convert cerrado to sugarcane, there is a carbon debit of 77, almost 78 megagrams of CO2 per hectare in the 30 centimeters. So let's calculate now the payback time. To do that, we use data from a very well-known paper by Fragione and colleagues, was published in 2008. And this data comes from that paper, 9.8 megagrams of CO2 per hectare per year as a sugarcane ethanol offset. So we are using this data from the literature, and then in our data with Fragione's 9.8 megagrams, we remember this data, we can calculate the payback time. So in this case, payback time for direct conversion of native vegetation to sugarcane is 8 years old. 8 years. The conversion of pasture to sugarcane, depending on the layer, 30 centimeters or 100 centimeters, we would have 2 to 3 years of payback time. And the annual crop, there is no payback time because we already are storing carbon under sugarcane compared to annual crop. So the payback time is 0. So to finish, because my time is finishing, we have a conversion of biomass carbon. When we have conversion, we are losing that, and the estimates show about 46 gigagrams of CO2 due to this conversion. In addition, we have the conversion, and we are losing carbon to the atmosphere, plus 3 gigagrams. So this gives us an yield net ecosystem emission of 0.7 to 1 megagrams of CO2 per hectare per year. If we take into account that we are using sugarcane to offset fossil fuel and using the value proposed by Fragione et al. Of 9.8, as you can see here, sugarcane is doing a very good job. So the conclusion is that Brazil is doing a significant role delivering ethanol with low carbon emission associated. So providing that ESALQ is minimized by improving management practice, and there is a lot of uncertainty around that, only take into account direct land use, we believe sugarcane ethanol is doing a quite nice job. More data and more details you can find in this paper published by Melo et al., our group here. And I take this opportunity to thanks again FAPESP for granting us and making this study possible. So thanks very much for your attention, and it's a pleasure to be part of this very important meeting.
Good morning. My name is Michel Colmanetti, and I will introduce you the study entitled Estimating Eucalyptus and Sugarcane Biomass Production in the State of Sao Paulo, Brazil, using a single and integrated process-based model, ECOSMOS, which was previously called AGROIBIS, which was developed in my postdoctoral at the University of Campinas between 2018 and 2020. This study is a section of a project entitled Characterizing and Predicting Biomass Production in Sugarcane and Eucalyptus Plantation in the state of Sao Paulo. This is a thematic project of FAPESP with a multidisciplinary approach that aims to support the regional carbon estimates for the two most important crops in the state of Sao Paulo. The modeling section is a work packet of implementation and calibration of a model dedicated to eucalyptus in an integrated simulator, ECOSMOS. After this implementation, it was possible to develop studies with the two most important crops in the state of Sao Paulo, sugarcane and eucalyptus. These two dominant vegetation types expanded significantly in the past 15 years, with large impact on the regional carbon balance. We expected this study will provide more accurate estimates of carbon gas emissions that potentially can be released by the land use change in the landscapes. The state of Sao Paulo is an important producer of sugarcane and eucalyptus. Just to give numbers, the state has more than 5 million hectares of sugarcane plantations, representing 55% of the total sugarcane area in the country, while eucalyptus has over 900,000 hectares of planted area, representing about 12% of the planted area in Brazil. So the state of Sao Paulo is the first and third most important producer of sugarcane and eucalyptus, respectively, in Brazil. Potentially, areas designated for one crop can be converted to another, changing the carbon balance and flux of carbon in an ecosystem. In this context, we have ECOSMOS, which provide robust estimates for sugarcane biomass. Using the new implementation for eucalyptus, we can estimate biomass and carbon for both crops using the same simulator. In this way, we minimize potential deviations, increase the precision of estimates, and reduce errors that are not directly associated to the performance of each crop. By using this simulator, we expected to have a better understanding of the carbon balance in the scenario of the land use change for both crops. Basically, the model runs using information of temperature, solar radiation, humidity, wind speed, and precipitation. Also, it's necessary to feed the model with information of water available in soil. When this information is not available, the tester is used to calculate it. If there is no climate information, we just provide the coordinates and the model will use its own database that is based on Xavier and NASA Power. The pedal transfer function are used to estimate the saturated upper limit, drained upper limit, and lower limit of plant extractable soil water. The saturated hydraulic conductivity is also calculated. As you can see here, the model has two canopies, the upper and lower, and different soil layer, where you can set up the size of each layer. The model's output correspond to flux, like net ecosystem exchange, sensible heat, latent heat, and evapotranspiration, and others. And the carbon stocks, like those in leaves, stem, and roots, for instance. I will briefly describe the methods and some results for the model's calibration and validation. Basically, we used the experimental sites to calibrate the physical and biophysical process to check out the functioning of the model. After, we performed a validation on a regional scale, demonstrating the effectiveness of the model in estimating the yield in different soil and climate conditions. So that it was finally possible to perform upscaling for the state of Sao Paulo. For calibration, we used extensively monitored sites. 4 of 5 sites, meteorological information with hourly time step was available. We also have a full information of the soil and information of the plant growth for each site. We investigate the physiological, physical, and biophysical process of the model. As you can see here on this picture, we have information of net hydration, net ecosystem exchange, and evapotranspiration. And we have in blue the observed values and in red the simulated values. We also investigated the water and soil, as you can see in this picture, and the biomass for the different components like steam and leaves, brent, coarse, and fine roots, for instance, as you can see in this picture. 1,335 plots of eucalyptus plantation were used to validate the eucalyptus submodel. The plot has different type of clones in different environmental conditions. Each plot could have more than one value of biomass along the years. So we not compare only the final production, but also the growth along the years, with an upper limit of 7 years old for each plot. We used the ECOSMOS database for climate and soil information to set up the simulations. As we can observe, we have a higher performance when compared to the simulated and observed values. A small overestimation for young trees and underestimation for bigger trees were observed for the simulated values. We did not observe difference between the clones or even between the different types of soil. For the validation of the sugarcane submodel, we compared the simulations obtained in the upscaling that I will next provide further details for the methods, with the historical average of the values obtained from the IBGE for the same simulation periods for 15 regions, or mesoregions, as I say in Portuguese, in the state of Sao Paulo. As you can see here, the observed values were slightly higher than simulated values, observed minus simulated, except by 4 regions, these and these 3 last one. Although the 3 last regions have the highest difference between simulated and observed values, we highlighted they are less important compared to the other regions. As you can see here, this is the last 3: Vale do Paraíba, Litoral, Sul Paulista, and metropolitan region of the São Paulo. Finally, to perform the upscaling, the simulations were set up using the climate grid of 25 by 25 kilometers square. Sorry, 25 by 25 kilometers. The soil water information was calculated from pedal transfer function for each soil type. We intersected the climate grid and soil information to obtain a total of 3,549 polygons. This is an example of an intersection of climate polygons and the different soil type inside it, as you can see here. Well, in this polygon, for example, we have 3 simulations that correspond to the intersection of the climate grid and soil types. And we have the information of the biome, here, Cerrado in this case, or neotropical savanna, the soil class, latosol or oxol, and the texture, in this case, argilla or clay. And finally, the curve number, which correspond to the topography. To include the climate variation along the years, it was performed a simulation with 4 rotations of approximately 7 years each. For eucalyptus and for sugarcane, we used 5 rotations with 1 planting and 4 ratoons for each rotation. Well, each polygon has an average weighted by the size of each soil type. As you can see here, we had average weight, in this case for the simulation 1, which correspond to the soil 1 times his percentage, and plus the simulation 2 times his percentage, plus, and finally plus the simulation 3 times his percentage, and finally we have an average weight. Finally, we have the upscaling maps, and as you can see here, on the left we have the sugarcane, and on the right we have the eucalyptus map. However, a large spatial variability was observed for both crops, and visually it was not possible to verify clear patterns of aggregation. The eucalyptus crop seems to be more productive in the south and less, as you can see here, and less productive in the north. The ratio of eucalyptus and sugarcane productivity indicates which region of the state one crop has higher or lower productive compared to the other one. We observed the great difference between crops in the north of the states, indicating the eucalyptus has lower productivity compared to sugarcane. These patterns are consistent with the physiological mechanism of these crops, where the sugarcane is better adapted to warmer conditions and regions with higher water restrictions. While in the south, southeast, and southwest, we have a smallest difference between crops, indicating the yield of eucalyptus seems to approximate to the sugarcane in terms of production. The conclusions, the sugarcane has higher annual dry matter biomass production than eucalyptus for most of the states of Sao Paulo, or all the states of Sao Paulo. Results are still preliminary, and different stocks, such as carbon in soil, for instance, must be investigated. It is important to highlight this is a study for development of a tool that can potentially quantify the effect of the land use change of the most important crops in the state of Sao Paulo. That can elucidate the real impact of this process on the ecosystem. I would like to thank the FAPESP for the scholarship and for supporting the project, the Microsoft, the Unicamp, Embrapa, Informatica, the NIPI, the CIRAD, the International Paper, the IPEF, and the ESALQ. Thank you all.